So we are preparing for upcoming test, and a question from section 1.4, similar to the questions in the text, but the slight twist to it is that suppose I have a matrix that is given to me A, B, C, D, E, F, G, H, I, and I think about an elementary operation, typically shown by a letter E, and here it's verbally described as a double second column. Question is write E as a matrix call that matrix E. How should E multiply A to have the desired effect? EA or AE. With matrix multiplication, we said we don't have the convenience that they will be the same thing. They are not the same thing. So some people said multiply. First of all, what is E anyway? Everybody saw that that is 1, 2, 1. Non-written entry simply means those are zeros. Now, I guess a couple of students said that we multiply this thing in this style. Is that right? Style 1, style 2. How many people for 1? How many people for 2? Who votes for 1? Let's see. 1, 2. Who votes for 2? 1, 2, 3. Okay. Well, you can always try, see what happens. Remember, we want the column. And if we multiply in this style, A, B, C, D, E, F, G, H, I, just go ahead and multiply. How do you multiply? Well, first and the last rows are just the original identity. They haven't been touched, and therefore they don't create any effect. Anyway, let's just do it. 1 times that is just A. 1, 0, 0 times that is B and C. And then when you take the second row, you're going to multiply it by each of these columns. Who is it going to be picked out by? 0 to 0 times A, D, G is going to create what? 2D, then 2E, and then 2F. Is that what we want? No, the very first row gave us a warning. You're not touching the columns. The column we wanted to double, it didn't. G, H, I. So it better be the other way then. So this is style 1. Style 2 is D, E, F, G, H, I. If you multiply it with 1, 2, 0, excuse me. Now, if you multiply with that column, now I'm going to take each of these rows, multiply by that, see the effect of the first row times that column is that it's going to pick out the A. Second row with that column is going to pick out the D. Third row with that column is going to pick out the G. When I do all of these things with respect to the second column of this, I see what I want is showing up, because ABC times 0 to 0 is going to give me what? 2B. And then this makes it 2E, and then this makes it 2H. And then the final one, we are multiplying by what is left from the identity. It's not going to make a dent. It's not going to make any difference. C, F, I is going to show up there. So if your elementary operations are to be done to the row or to the column, it's a different style of multiplication that you carry out later on, and that's something to live with the matrices. Simply these two are not the same, and you have to be careful what kind of operation do you have in mind. Now let me see if you have any questions from problems 1 through 15 on section 1.4. Any question? We started talking about yes.
I did have a question, but it was actually from 1.3 and 37.
One.
It was just a general question. It asked that there was 3 parts, and the second 2 parts was to multiply by column expansion and then by row expansion. And my question is that the answers from those 2 shouldn't be the same, right?
They all should. We are multiplying the matrices, and we said there are many different ways of multiplying, essentially based on how to create blocks and go by certain format of going through the blocks. So all of your matrix multiplications have to result in the same answer, of course. So problem 37 through 42 says find the product of the given matrices by using this definition or the other definition or some other definition. They all have to be the same thing. Like, no, which one do you want me to do?
Well, just the second 2 parts, multiplication by column expansion and multiplication by row expansion. I got 2 different.
Okay, let's see. Let me first refresh my mind. What does the book mean by column expansion? It says follow example such and such. So your question is with respect to 37. Is that what you want to do? So we have 2 matrices, A, 2, minus 1, minus 1, 3, and B, which is 1, 2, 4, minus 1. The question is, what is AB? And then it is asking you to do it by following one of many different examples. One of them is expansion by columns. And then expansion by rows. That's example 11. And the outer products, that's example 12. Okay. Expansion by columns says, so we have 2, minus 1, minus 1, 3. We are multiplying with 1, 2, 4, minus 1. And the question is, do you pick these rows multiplied by that column and the next column, or do you pick this row multiplied by this column and the next column, and then you go to the next set of activities? Let me just make sure I understand the book correctly as to what it means by expansion by rows. So this is here, what the book wants you to do. Expansion by columns means you take this entire matrix, multiply by this column, and then once you are done with that, you go through the next column and so on. So let's go ahead and just perform this. The notation that the book uses is, let me tell you what I'm going to do. So I'm going to take 2 minus 1 minus 1, 3, and multiply this one with the column 1, 4. We have to carry this out, and then we are going to have another piece. We are going to do again a similar thing, which is take 2 minus 1 minus 1, 3, multiplied it with the second column, which is 2 minus 1, and when you are all done, you have just a 2 by 2 matrix. So how do you do that? Well, just based on the definition, what do you get? 2 times 1 minus 1 times 4. And what do we get out of it? 2 and minus 4, so I get negative 2. And then I multiply this one, so I have minus 1 and 12, so I suppose I get 11. Is that right? Then you carry this one out, say 2 minus 1 times 2 minus 1, that's a 5. Minus 2 and minus 3, minus 5. So the focus here is to chop up the second matrix as a bunch of columns and treat them as one column at a time. Example 11, let's see, I can maybe squeeze it right here. So we get 2 minus 1 minus 1, 3, and then again we are multiplying with 1, 2, 4 minus 1. The view now is that I am going to chop up my first matrix as a bunch of rows, multiply each of these rows with this entire matrix, and perform my operation in that style. So what I'm going to keep in mind is that I'm going to take 2 minus 1 So when I multiply this with this matrix, I'm going to get a row. Let's indicate how it's going to be laid out before we do it. So 1, 2, 4 minus 1 is going to be one row of my answer, and then I have minus 1, 3 multiplied by 1, 2, 4 minus 1, and then we are going to carry this out. So how do you do that? So you say just multiply. You take this row, multiply by that column, exactly what we did there, 2, and minus 4 is minus 2, 4 and minus 1, what am I going to have? 5. Now I process the second row times the same second matrix. Minus 1 and 12, 11, minus 2 and minus 3, minus 5. So this is the second style of doing this thing. And third style, which is outer products, it's kind of more interesting, is, so I have now 2 minus 1 minus 1, 3 times 1, 2, 4 minus 1. I want to write these things with outer product style. So this, let's write on top of it, this was a row expansion. This one is column expansion. So I understand what the book means. So column expansion means create one column at a time. Row expansion means create one row at a time. Outer product, we talked about this thing more extensively. We said this is the multiplication style creation of the result. What do we do? Which matrices, which rows and columns are going to be multiplied? Take this first row, multiply by what? The first column multiplied by the first row, and then second column with second row, and create multiplication tables out of them and add them up. So what we do is, so we are going to have 2 minus 1 times 1, 2 plus minus 1, 3 times 4 minus 1. This is the outer product. How do you multiply it? We call this multiplication table style. matrices just looks like the stuff you had done in school. So you multiply, think about it like this, like you have 2 minus 1 on this margin and 1, 2 on the top margin. You just multiply all the entries. So you get 2. What do I get here? 4. Now I get minus 1 multiplied by the same thing. I get what? Minus 1 and negative 2. Do the same thing with the second entry. So that multiplied by all of this, that multiplied by all of that. So what do I get here? Minus 4 and 1, and here 12 and negative 3. Okay, so you multiply. This is your left margin, that is your top margin. You multiply everybody with everybody, and then these are the contributions. You add them all up. So 2 and minus 4, 4 and 1, minus 1 and 12, minus 2 and minus 3. So you notice that, of course, we better have same answer. Is that right? And these are our answers. And we said the objective of all of this is well, in reality, people deal with huge matrices. The matrix has to be chopped up, either because naturally it's chopped into pieces, or because you are doing a lot of computation. You want to use all of your resources all at the same time. You don't want one section of a computer wait for the other section. You want to keep all the cores busy, and so you cut it up, and then you send it to different processors and process it differently. That's just a beginning of that kind of an idea. But in many cases, it is naturally present because the physical problem you're dealing with, it is naturally broken up into blocks, and then you deal with block by block. These are just three of these styles. There are still other ways of multiplying. Problems usually, the natural problem tells you what's a natural way of multiplying your matrices. Anyway, any other question? Well, if it's the same question, then I expect all the 3 pieces there. So here's my row expansion, here's my column expansion, here's the outer product. So let's keep that as a standard that we expect everybody to go by. So row expansion, we said here what it means. We are creating a row of, the row means row of the final answer. You're creating it a row at a time. This one was a column expansion. You're creating the final answer a column at a time. And outer product, you're creating it by breaking it up into tables, creating separate tables, and then putting them together. But if a matrix is given, it's multiplied, you just go ahead, whatever is comfortable to you, that's just what you do. Okay. Next question.
So if you have matrix A, and you times it by its inverse, that's going to be any matrix that would give it the identity, right? That's what an inverse matrix is?
Yeah. The definition of inverse of a matrix is that if you multiply it by the original, however you multiply it, you get identity. Yes. Any other question? So everybody feels comfortable about the test coming up? Well, you should. We are going very slow, and all the exercises are basic. It's just that you need to do a lot of these multiplication until it becomes second nature. It's like there's no way of getting around all those exercises you need to do until you just feel comfortable about what's going on, and you can double check your own activities, make sure errors don't happen, can catch yourself. This question, for example, tells you how to double check yourself. Try 2 different styles, make sure they match up, and so for the test, make sure you understood the application of matrices to substitution, the idea of substitution. So substituting a variable for another one turns into a matrix multiplication. We learned about that. We talked about some application in business when you want to create revenue and cost and such tables. You have to end up multiplying meaningful matrices. The only question of all of these things that you have done that requires quite a bit of thinking, or at least a little bit of thinking, was the fact that matrix multiplication is associative. That if you understand it as a substitution, it's a lot easier. If you want to show it by multiplication, it's a bit messy. Okay, we were talking about elementary operations. We were talking about, we said that 3 elementary operations. You can either interchange rows, or you can multiply a row by a number, and the third one was what? You can add multiple of a row to another row. The other first two we tried. The third one we want to talk about today, elementary operations, as matrix multiplication. Well, before we get ourselves buried under all this gymnastics and pushing numbers around, let's see what is the philosophy of this. What is it that you're trying to do? We said Gaussian elimination is a big deal in linear algebra. That's what you live by. It's like the main staple of linear algebra. So Gaussian elimination was talked in terms of, well, you are doing elimination of certain numbers in a matrix. We are trying to make it more formal. Say, okay, you are carrying out 3 kind of activities during Gaussian elimination. If we can write them out in linear algebra language, which is matrix multiplication, things are going to be a lot easier for us to track as to what is really going on, and also prove lots of basic ideas. So we had 3 operations. We had the operation of exchange of 2 rows, that when it came to matrix multiplication, that gave us idea of permutation matrices. We had a special notation for it, Pij. It meant this is a matrix that exchanges row I and row j. What was Pij? Pij was same as the identity matrix, except that its row I and row j have their entries exchanged. So if this is row I and the column j, excuse me, row I and row j, and here's a row row I and row j are going to be here, column I and column j is going to be here. And the identity, there's going to be a 1 in this location and 1 in this location. Is that right? On the identity, for the identity, there's a 1 here and there's 1 here, and of course there's 1 all over the place. When we want to make a permutation matrix, what did we do? Yeah, these guys turn into zeros and they switch their places with these locations. Everything else stayed intact, so we didn't do anything to that. Then the elementary operation number 2 was multiply a row by a number. That one gave us some matrix M, let's say M for multiplication. And if your row is, say, row I, the corresponding matrix for this thing, what did it look like on the row I of it? So everything else is just 1 on the diagonal, except that in this location, what entry do we see? Whatever number. So if this was number M, in that location you see that number M, everything else is same as before. So these things are stuff we practiced last time. Now for a more interesting one, item 3 is add multiple of a row to another row, so let's call this multiple M and the original row I, and the row that is going to be changed, call it row J. And a notation for such a matrix, let's see if the book has any standard notation for it. Well, we ran out of things, so let's call it E. We want to figure out what does this one look like. We might as well go ahead and practice some basic things, see if we can guess what the final answer is going to be. So let's just hold this for a moment. Suppose I have a matrix A, B, C, say D, E, F, G, H, I, and what I want to do to this is to add double of the first row to the third row. Well, if I do that, what do I get? I want to add double of the first to the third. So what does the third one is going to look like? 2A plus G, 2B plus H, and 2C plus I. Is that right? Verbally explaining our activity is easy. Double the first row and add it to the third row. Question is there a matrix that multiplication with that will have exact same effect? So here is a question. Is there a matrix that if I multiply on the left with this guy, the result is what I want? If that is so, then finishing all the Gaussian elimination activity, and every single one of them can be represented by matrix multiplication. That's going to create a very clean way of expressing what Gaussian elimination is all about. Well, the first two rows are untouched. That gives me a hint that the first two rows of this mystery matrix are going to be what? Untouched identity. So now there was something that we noticed in the previous two, that to create that matrix we apply the same activity to the identity. Whatever comes out of it, that's going to be the matrix that if you multiply by any matrix, is going to change it in the same style. So with that in mind, what do you think should be the entries of the third row? Okay, if you take an identity matrix, if you have an identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, and I apply this idea of add double of the first to the third, adding double of the first to the third row is going to create a 2 here. And what we are saying is that once you do that to the identity matrix, the resulting matrix, if it is multiplied by anybody, has exactly the same effect. Well, let's go ahead and check to see that this is really so. Well, here are my zeros. So 1, 0, 0 multiplied by any of these columns is going to just copy ABC over. Second row multiplied by this is going to just copy the second row over. The last row is where things become interesting. So I have 2, 0, 1. When I multiply by this column, what does it do? Doubles the first, adds it to the last. That's exactly what we wanted, or to the third. Same applies to each of these columns. So it doubles the first entries and adds it to the third entry, so it does exactly what we want. So now suppose you want to go backward. Okay, suppose I want to go this way. What should I multiply this one with to undo the damage? So I suppose I have A, B, C, D, E, F, 2A plus G, 2B plus H, 2C plus I. Is there anybody that if I multiply with this on the left of it, I go back where I came from, A, B, C, I have to undo this damage. While undoing this damage, how do I undo it? I want to get rid of the 2A and the 2B and the 2C. I have to take a copy of this to add to the third row to get rid of all this yellow stuff. What multiple of the first row should be added to the third row to do that job? Yeah. So opposite of adding double is subtracting double. So subtracting double, same principle as before. So subtracting double of the first row from the third row. So the meaning of this would be subtract double of first row from third row. Well, it makes sense that the number here has to be -2. What does that tell us about these two matrices? So I have this matrix here and this matrix here. What's the relationship of these two to each other? They are inverses of each other. So that's an important fact, that not only these elementary matrices are easy to create, but also their inverses are very easy to just cook up. We don't go through a huge torture just to create the inverse, which is typical with the ordinary matrix. Ordinary matrices take forever to find their inverses, but these guys, let's check. So I multiply with this this row with this column and that one. The result is not any unexpected activity. Second row with any of these things, again, we don't have anything special happening. The only thing special to look at is what is the product of this row and that column. What is the product? Well, what is exactly the product of this yellow row with this yellow column? 2 minus 2, I get 0. In the other location, I wasn't expecting anything anyway. When this is multiplying the second column, 2 is going to be cancelled out. Third column, same way. So these locations, the result is not so surprising. What is interesting is that entry turned out to be 0. So these two matrices do reciprocate each other. They become opposite of each other. So let's just quickly review what is the inverse of each of these matrices we have talked about. So let me see if I can ask you to quickly write the inverse of each of these matrices. So I wrote a matrix. The idea is that you recognize it quickly, and can you tell me what's the inverse of it? It's the same thing. This is first of all, you recognize it's a permutation matrix. This is a guy who exchanges the second row with the third row. Its inverse is just itself. I don't need to spend any time figuring out that. You can always double check quickly. Second type we saw is multiplication types. What's the inverse of that one? Just 5/3. Notice how different activities are. There, nothing happens. Here, the number is turned upside down, and what we saw just right now is that if I have What's the inverse of this one? Positive 5. This the activity of I don't know, are we talking about this one? This is adding minus 5 times the second row to the third row, or subtracting 5 times second row from the third row, and so on. So you notice that matrix inverse activity is not something that can be easily guessed at by just looking at a bunch of numbers. The activity is so different. Here, perhaps what you remember from inverse from elementary school, that is shows up here, but no such thing showed up over there. And the fact here is the sign switched over, and they are all very different. So hopefully you don't think that inverse of a matrix is made out of the inverses of the individual entries. Such a thing just doesn't have any place. What is the inverse of that? You have to keep in mind that it's going to take quite a bit of effort for us to figure it out. It's not something that can be guessed at. What is our strategy? Our strategy is apply apply the Gaussian elimination to this until it becomes identity. So here we start with this guy. Here's our, let's call this is a matrix. Suppose you want to find the inverse of it. So this is A, and you're asking what is A inverse. We are going to start with A, and then apply this kind of these operations that we learned. We are going to apply those operations to our matrix one by one. Those applications we learned that they can be represented by matrix multiplication. So whatever it takes, we are going to apply it. So here I might say elementary operation number 1, whatever applies. Then elementary operation number 2, elementary operation number 3, and perhaps I need to apply so many times, say 10 times, 100 times, whatever it takes, until I have essentially moved down all the numbers and reduce my matrix to an identity. So we can just keep applying these elementary operations until finally what is left out of a matrix is just an identity matrix. What is so great about such an achievement? The great thing about it is that I can undo the process and remember, the matrix that multiplies an existing one to make it identity has a name. What is this thing anyway? That has to be inverse of that. So by breaking the job to step-by-step Gaussian elimination steps, we can also create our inverse. The process is going to be rather laborious, but it is at least definite as to what it is. Now, the way this is actually written out in the exercises, or the way it is done in the text, is that we write our matrix. Right next to that, we are going to write the identity matrix. Then we apply these operations that we think is going to clean up the scene for us. So I apply the operation like E1 to this matrix and write the result here. So I keep a space here and I'm going to write my entries here. Then I go to the next entry, E2. E2 is going to be applied to the previous one. E2 applied to this. I'm going to write the matrix again underneath it, and so on. Every time I'm going to apply one of these operations and I'm going to copy the matrix down here. So at the very end of this process, I will have the final result of applying E10 to whatever I had in the previous stage until I have hopefully my identity showing up at this stage. So identity shows up here. What do I do here? Well, I want to also create A inverse. So how do I create it? I take E1, the matrix E1, I multiply it by the identity. Then I multiply it with E2. Then I multiply it by E3 all the way until I multiply by the very last one. And whatever this is, that has to be my inverse. So once I am acting on the matrix A to create something else, I am also going to pick up the identity and do the same thing to the identity. So I have E1 applied to the identity. I'll keep a track of it here. Then E2 applied to whatever I had before is going to show up here. Until at the very end, E10, E9, and so on, all the way to E1 applied to identity is going to be here. And then what is going to show up at this stage is just our promised A inverse. Oh, perhaps I didn't make it clear. Let's just go ahead and pick up one example matrix and find the inverse for it. And I guess not today. Okay. So what we are going to do on Wednesday is to carry out this process on some examples. So for Wednesday, that's what you want to do. For exercises, let me tell you for the okay, so for Wednesday, what you want to do is whatever exercises from 1 through 24 that shows up on your blue sheet, you want to make sure they are all done and ready to go, and then we are going to take it up and continue. Okay, if you have any question about any of the problems and you want to ask me, I'll stay over a few minutes and answer your questions. Good luck and God bless.